Hello, welcome to ATG 4950. This session will address reliability and maintainability engineering. Reliability and maintainability attempts to study, characterize, measure, and analyze the failure and repair of systems. These measures will be used to improve systems' operational use by increasing their design life, eliminating or reducing the likelihood of failures and safety risks. Actually, they are pushing, everyone now is pushing for reliability and maintainability to be within the design stage. And that's why we are interested in this one, because we would like to encounter that or to include it in the design of the product. And that will reduce system failures and will reduce downtime, thereby increasing available operating time or product availability. When buying a new product, usually we look at the warranty associated with it or the possibility of buying a maintenance plan. But the maintenance and reliability is not only important for the customer, but also important for companies. Maintenance and reliability can affect companies' operation. If one of the main machines broke in manufacturing environment, the company or the company's operation will be affected, and employees might be idle until fixed. The reputation of the company, if the reliability of the product or the maintenance are not good, that will affect the company's reputation and will cause customer loss. And the profitability. With profitability, we look at the operation that's been affected, which were caused by customer loss that will lead to decrease in the profit, and maybe profit becoming losses instead of gaining money. And also the ability to protect investment in plant and equipment, the ability to provide a safe workplace and impact the environment responsibly. Now remember also, for your product, if you are designing a product, you would like to have maintenance associated with it or maintainability capabilities. The easier it can be maintained, the more appealing for the customer, the more reliable, the more appealing for the customer. So whether it's we are talking about companies machines or companies production, or we are talking about the product itself when it comes to the design stage or design for that product for life cycle. Maintenance is defined as all activities involved in keeping systems, equipment in working order. For us, maintenance, we are looking at a product that can be maintained easily. If the parts are available in the market, then it can be replaced. It can be maintained, and it will last more than other products. Especially if we are talking about products that are expensive, that goes all the way to like $300, $400, $500, maybe $1,000. At that point, you would like this system to be maintainable, and the parts are available in the market. While when we talk about reliability, it's defined as the probability that a machine will function properly for a specific time. The objective of the maintenance and reliability is to improve systems' operational use by increasing their design life, eliminating or reducing the likelihood of failure while controlling costs. Some of the tactics that can be followed to ensure better reliability and less maintenance. In reliability, we need to improve individual components by increasing their reliability, which will lead to the increase in the reliability in the whole or the overall system. Whatever we select as components, it has to be with high quality and reliable components, and that will reflect on the overall system. Providing redundancy or having parts ready to replace existing parts in case of failure will also ensure an operational system or an operational product that we have. In the maintenance part, we need to do a preventive maintenance or create a plan for preventive maintenance, which should be implemented to reduce machine breakdowns. If a machine breaks down, the repair capability or speed should be increased to bring the machine back to its operational condition as fast as possible. And again, this is from like a machine in a factory or in a production line operation or capabilities, but at the same time we are talking about a product that we would like it to be up and running. I bought that product, I would like to make it up and running and functioning all the time. So it's good to have a maintenance plan that will assist me in getting the parts, replacing the parts, maintaining, cleaning, changing some stuff, so it will stay as long as possible functioning as needed. To calculate product failure rate by percentage, we divide the number of failures by the number of units tested, then multiply by 100 to calculate the failures or the failure rate by number. We divide the number of failures by the number of unit hours of operating time. So now we have the failure rate in percentage and the failure rate in number. From that we can calculate the mean time between failures, which will equal to 1 over failure rate, the one with numbers. So that will be the mean time between failures. In this example, we have 20 air conditioning units designed for use in NASA space shuttles operated for 1,000 hours, which means that the total number of hours that those machines should operate is 20 times 1,000, and that will equal to 20,000 operating hours. So if one failed after 200 hours and one after 600 hours, which means that those two operated 800 hours instead of operating 2,000 hours. That's the difference of 1,200 hours that need to be subtracted from the 20,000 to get the actual unit hours of operations. So whatever failure is, we need to subtract it, and that will be the total operating hours. Based on that, we can calculate the failure rate as a percentage, which will equal to 2 over 20 times 100, and that's 10%. The failure rate based on the number of operating hours will equal to 2 over 20,000 minus 1,200, which will equal to 0.00106 failure per unit hours. And the mean time between failures will equal to 1 over 0.00106, which will equal to 9,434 hours. So we expect that the time from failure to a failure will be 9,434 hours. That's what we expect from our calculation. That's where we plan for a maintenance. At maybe 9,000, we can maintain before it breaks, so we can keep it up and running for another 9,434 hours and so on. So before it breaks, before it reaches to that point of failure, we can plan for maintenance. Failure rate per trip will equal to the failure rate per number, or in numbers, multiplied by 24 hours, multiplied by 6 days per trip, and that will equal to 0.153 failures per trip. To reduce the failure of the system, we need to reduce the failure of the components. Improving individual components will increase reliability of the system. but there are two ways to connect the components. If the components in series, the system reliability will equal to the multiplication of reliabilities of the individual parts or components, which will equal to R1, R2, or all the way to Rn. So it will be R1 multiplied by R2 multiplied by R3 all the way to Rn, and that will be the reliability of the system. Assuming that here that R1 is the reliability of component 1, R2 is the reliability of component 2. As components been added to the series, the system reliability will decrease. This figure shows how system reliability decreases as number of components increases. To understand more, let's look at the following example. If we have a process or a product that has 3 components with reliabilities of 0.9, 0.8, and 0.99 respectively, the overall reliability will equal to R1 times R2 times R3, which will lead to an extreme decrease in the overall reliability to 0.713 or 71.3%. If reliabilities of systems components are equal, then system reliability will equal the reliability of components to the power of the number of components in the system. It's the same value, so we don't have to keep multiplying 10 times, 20 times, 100 times. We just can say that the reliability of the system will equal to R of 1, or the reliability of 1 to the power of the number of components. If it's 20, it will be 20. If it's 100 components, then it will be to the power of 100. If a system consists of 100 components connected functionally in series, each component has a 100-hour reliability of 0.99. So in this example, we have 100 components. Each one has a reliability of 0.99. They are all the same, they are all similar, and has the same reliability. Calculate the reliability of the system. Since n is equal to 100, the reliability of a component is 99% or 0.99. Then the reliability of the system will equal to 0.99 to the power 100. The reliability of the system will equal to 0.366 after calculating that value. The unreliability of the system will equal to 1 minus. Remember that it's a probability. So when we say that it's 99% reliable, then it's 0.01% not reliable. 99%, then it's 1% not reliable. 99% reliable, 1% not reliable. So if the components reliabilities are equal, then the unreliability will equal to 1 minus the reliability of one component to the power of n of these components. If the components reliabilities are not equal, then the unreliability will equal to 1 minus the product of all multiplied reliabilities. If the components of the system were connected as a complex set of interrelated components in such a way that a standby part can take over the function of a failed part to save the system, then at that point the system will be called a parallel or a redundant system. They are connected on parallel. The components are connected on parallel, or what we call as a redundant system. In the parallel, the overall reliability of the system will equal to 1 minus the reliability of the first component multiplied by 1 minus the reliability of the second component, and so on until we get to the nth component. When a component does not function, the system continues to function using another component until all parallel components do not function anymore. Some of the facts in parallel systems is that system reliability will increase as the number of components increases. Marginal probability refers to the increase in reliability as components are added. As redundancy increases in parallel systems, it's important to balance the cost involved. The cost of adding another component must never be greater than the benefits received from the increased reliability. When providing a backup for a component, basically we are adding the probability of second component working multiplied by the probability of the needing a second component. Adding that value to the original probability will increase the overall probability to, in this case, in our case, to 0.96 or 96%. So the actual one was 80%. Adding 16% increased the reliability to 96%. And that's again because of the redundancy that we provided, the standby part that we provided. So as soon as one fails, the other one will take over and will continue functioning as needed. To increase the reliability of the system, in the previous example, we added a replacement part, which means using redundancy to improve system reliability. Remember, we calculated that as the reliability of the system as 0.713 or 71.3%. So adding for R1 and R2, adding another one with the same reliability, that means that in case one of them fails, there is one that will take over. And by doing that, we have now parallel for R1 and R2, or standby for R1, R2. Recalculating using the formula of the parallel component, the reliability of the system will increase from 71.3% to 94%. And you can see the calculation in this slide. Real-life systems include a combination of series and parallel components. Not all systems will be connected in parallel. Not all of them will be connected in series. So most likely you will find a combination of both. The reliability of the system can be determined by computing the reliabilities separately using the rules that apply to either series or parallel. So if we have the parallel, we can combine the parallel to get only one reliability, and then we put them all in series and multiply those values to get the reliability of the system. If it's the other way around, then we finish the series first and then we do the parallel. So it depends on what kind of system and what kind of combination we have. We can do it level by level until the entire system is completed. The example in this figure shows a combination of series and parallel components. The C component can be replaced by one reliability through the redundancy approach. So we added another C, another reliability or another component similar to C. In case that C component that we have failed, another C component is there to it's standby and it's redundant to take over and continue operation. Then A, B, C prime, or the new C, and D will be calculated as series. So what we did, we replaced the two parallel C's with one C prime, and the C prime now it's in series with A, B, and D. Then we use the formula for the series to find the reliability of the system. Facts for the series parallel systems: as the number of components in the series is increased, the system reliability decreases or at an increasing rate, as it is in the series alone. For any series system with more than 20 parts, the part reliability must be greater than 95% for the system to have much usefulness. Otherwise, it will not function with very low reliability. As the number of parts increase, the part reliabilities must be increased in order for the system to have a reasonable level of reliability. One of the main objectives of increasing reliability of the system is to reduce the frequency of maintenance. As time passes, the reliability of the system will decrease and maintenance frequency will increase. The unreliable systems will usually require extensive maintenance. Maintenance is the process of repairing and or replacing of the failing component. Companies perform maintenance to increase the probability that a system will continue to operate efficiently, knowing that there will be downtime associated with the repair process. The goal of the maintenance is to return to a failed or deteriorating system to satisfactory operating state or to its functioning state. There are two types of maintenance. You can monitor and service the part before it breaks to keep facilities operating efficiently, and this will be called preventive maintenance. And this is what we meant by knowing the mean time between failures. Then you know when would it fail the next time, and if you do that, you plan for preventive maintenance. You plan for that maintenance. Or you can wait until the component breaks or fails, then fix that component, and that will be called corrective maintenance. Reliability of the component and the system will assist in identifying the frequency of required service. Components will have an initial failure rate known as infant mortality, then will follow a normal distribution until it starts declining at the end of the product life cycle. And this is, we know that at the end of the life cycle of a product, it will start declining, needs more maintenance, it will not function as it was the first time. So all that will be a failure or failure of component, which will reduce the reliability of the system. Identifying the mean time between failures and documenting possible breakdowns will aid in increasing or in creating a preventive maintenance schedule to increase or to bring reliability back to its normal and to keep the system functioning as needed. Waiting for the part to fail might affect other components and cause a greater damage to the overall system. A corrective maintenance might cause longer downtime and more money to fix. If it needs repair, major repair, because of a corrective maintenance, then that will be a downtime for or idle time for the employee, for the machines, for the production line, and more money will be needed to fix that production line to bring it back to the state that it was in before. Maintainability requires a confidence limit to provide reasonable assurance of accuracy. The faster the repair, the faster the system will go back to its regular performance level. Maintenance will involve labor hours and cost factors. There should be a balance between preventive and corrective maintenance. You need to perform preventive maintenance to protect the system from breakdown or a major failure, but at the same time performing too often maintenance might cost a lot. At the same time, you don't want to ignore preventive maintenance because that might lead to a major breakdown with large cost. The true total cost of breakdowns will include having components in your inventory, the cost associated with employee morale, and the cost associated with the unreliability of the scheduled maintenance. In the traditional view of cost, by increasing the preventive maintenance, we decrease the breakdown maintenance, which will bring the total cost to its lowest value, then starts increasing again. The lowest total cost will not be the point where preventive and corrective maintenance meet. So even with the preventive maintenance, we have to be careful not to exceed the limit, otherwise that will affect the total cost, and you will have lots of items in inventory. You are planning for lots of maintenance, that's maintenance labor hours, which will increase the overall cost. So we have to be careful and balance when to do preventive maintenance, how many times do we do preventive maintenance, and make sure not to reach to the point where we need major corrective maintenance and major cost. While in the full cost view, taking into consideration all factors, the lowest point will be after the intersection point. Currently, and with the new technology, most companies use computerized maintenance system to monitor and see how the system improves or work. The system will have data that includes equipment file with parts numbers or parts list, maintenance and work orders or work order schedule. We have also in the documentation repair history. We have inventory of spare parts, personnel that will work or who will work on the machine or the fix, and their skills and wages, other related information to the maintenance program, and that will assist us in calculating the overall cost. So all that will be collected, reported, and considered in the total cost analysis, which is very good. Now we understand how all these factors affect the maintenance and affect the reliability of the system. And based on that, we can calculate the total cost and find the optimal point for maintaining or creating that plan for maintenance and the frequency of the maintenance. So all these reports can assist in taking the proper decision and developing the proper strategy or a maintenance plan based on the identified optimal point. Let's look at an example. A company that would like to have printing capabilities, but they don't know if they need to contract some companies, some third party for maintenance, or they just do it themselves. They looked at the number of breakdowns, at the number of months that breakdowns occurred, and they got the table shown in this slide. The average cost of breakdowns is $300, and that's for a breakdown to be fixed. It's $300. Computing the expected number of breakdowns by finding the frequency, then multiplying that by the number of breakdowns, then finding the sum of the incidents, will result an average of 1.6 breakdowns per month. 1.6 breakdowns per month. If the average cost of a breakdown is $300, then the expected breakdown cost per month with no preventive maintenance will equal to 1.6. Those are the 1.6 times or breakdowns, multiplied by the cost per breakdown, which is 300, and that will equal to $480 per month. And this is what they need or they're gonna spend on maintenance per month if they did not use a contractor. If a service contract was signed with 150 per month, the average number of breakdowns will be 1 breakdown a month. Computing the cost of preventive maintenance, which will equal to the cost of expected breakdowns if service contract signed plus the cost of service contract will result 450. The breakdowns per month will equal to 1 multiplied by 300 plus the 150 the contract value, then that will be 450 compared to 480 with no preventive maintenance. 450 is cheaper, so the decision should be to hire a service firm to maintain the machines. To increase repair capabilities, the company needs well-trained personnel, adequate resources, ability to establish repair plan and priorities, ability and authority to do material planning, ability to identify the cause of breakdowns, and ability to design ways to extend the mean time between failures. This figure shows how maintenance is performed, where you can see the preventive maintenance cost less and is faster moving to the left, while competence gets higher if we moved to the right. Total predictive maintenance is a method for improved machine availability through better utilization of maintenance and production resources that was introduced in Japan in 1971. This method includes designing machines that are reliable, easy to operate, and easy maintain, emphasizing total cost of ownership when purchasing machines, so that service and maintenance are included in the cost, developing preventive maintenance plans that utilize the best practices of operators, maintenance department, and depot services, and then training workers to operate and maintain their own machines. We can also establish maintenance policies using simulation and expert systems to analyze complex situations, model different maintenance programs, and select the proper model that fits the needs of the company with the lowest cost. Expert systems will be utilizing advanced computing capabilities to identify problems and select the proper course of action. Maintainability can be measured using different measures to ensure lower and efficient operations. Some of the common measures are the mean corrective maintenance time, the mean preventive maintenance time, the median active corrective maintenance, the mean active or the median active preventive maintenance, the mean active maintenance time, the maximum active corrective maintenance time. In addition, we can use other measures that are related to other factors such as logistics delay time, administrative delay time, maintenance downtime, maintenance labor hour factors, maintenance frequency factors. We can look at the mean time between maintenance and mean time between replacements. And then the last one is maintenance cost factors. That will be all for this session. If you have any questions or concerns, please let me know. Thank you and have a great day.